So, 9 months.
Great.
That is what's a full human gestation period.
Yeah, it is.
But it's also apparently how long high-end physics experiments used to take just to process their data.
Exactly. You run the experiment, and then you just sort of wait 9 months to even see if it worked.
Right. And this week, we saw that timeline just completely collapse from 9 months down to 4 hours.
4 hours. It's wild. It represents a workflow reduction of over 99%.
Which, I mean, it sounds like a typo in a press release.
It really does, but it's a verified metric. It's coming out of this intersection of GPU computing and linear accelerators. And I think it perfectly sets the tone for everything we are going to be covering today.
Absolutely. So welcome back to the deep dive. For this discussion, we are looking exclusively at NVIDIA's research and announcements published between February 9th and February 15th, 2026.
Just that 1 week.
Just that 1 week. And honestly, looking at the pile of sources you brought today, we've got robotics, compilers, tokenomics. It feels like the headline isn't just, faster chips.
Right. We've heard the faster chip story before.
Yeah.
The chips are faster, sure. But the real signal this week is the shift from brute force to extreme optimization.
Okay.
We are seeing these hardware taxes, basically the unavoidable cost of doing business in AI turning into software advantages.
Meaning what exactly?
Meaning we're talking about slashing inference costs by 90%. We're talking about automation that takes these PhD-level deployment tasks and turns them into a simple click-to-run process.
So we're essentially moving from how do we build this massive AI to how do we actually use it without going bankrupt?
Exactly. It's the industrialization phase for this technology.
Let's start with the physical world then. Segment A, Research and Robotics. There was a story on the NVIDIA technical blog on February 10th. The headline was R²D², Scaling Multimodal Robot Learning.
A bit on the nose with that acronym, I think.
Very much so. But this is a global release, and what happened here is that NVIDIA released this digest focusing heavily on Isaac Lab.
Right, which is their GPU-native simulation framework for robot learning.
And the reason this matters, the metric they dropped regarding training throughput is just staggering. But it needs some context.
It does. So, for humanoid locomotion, they hit 135,000 frames per second.
135,000.
Yeah, and over 150,000 frames per second for manipulation tasks. So like a robot hand learning to pick up a coffee cup.
Okay, contextualize that for me. Because, when I play a video game, I'm perfectly happy with 60 frames per second. Why on earth does a robot simulation need to run 2,000 times faster than that?
Because the robot isn't playing for fun. It's undergoing hyper-accelerated evolution.
Okay.
This directly addresses what we call the sim-to-real gap. The real world is incredibly messy. Floors are slippery, light refracts off windows, your sensors have static noise.
Right, the real world is chaotic.
Exactly. So to teach a robot to handle that chaos without breaking a $2 million physical prototype by making it fall over 1,000 times, you have to run it through thousands of variations of reality and software.
Sort of a multiverse approach.
That's a great way to put it. Isaac Lab is now supporting 4,096 environments simultaneously.
Wow.
So that means over 4,000 parallel universes running at 150,000 frames per second. It can experience literally 1,000 years of trial and error while you take your lunch break.
And it's not just visual data either, right? I read they integrated multiple modalities.
Yes, these environments have full RGBD sensors enabled. That's standard color vision plus depth perception. And it's all synchronized with proprioception.
Proprioception, that's the robot knowing where its own limbs are in space.
Correct. So the simulation is fusing vision, depth, and body awareness all at supersonic speed. It fundamentally changes the iteration cycle for roboticists.
Because if you tweak, say, the ankle joint design,
you can retrain its entire walking algorithm instantly just to see if that physical tweak actually works.
that is incredible. But, speeding up the body is really only half the problem. You also have to speed up the brain, which brings us to another research story.
The QuRL paper.
Yes, QuRL. This was published on RSViv on February 15th, and it was accepted to ICLR 2026.
Stands for Quantized Rollout.
Right. And what happened here is they found a way to speed up reinforcement learning for large language models.
Which is huge.
So why does this matter? Let's break down the bottleneck first. What exactly is a rollout?
Think of the rollout as the brainstorming phase. When you train an AI using reinforcement learning, let's say you wanted to solve a complex math proof or write some efficient Python code, the model has to explore different paths.
It has to try things out.
Right. It tries option A, option B, option C, just to see which one actually yields a reward. That exploration process is the rollout.
And I assume that's computationally very expensive.
Oh, incredibly.
Right.
It takes up to 70% of the total training time. The model is just churning through possibilities, and most of them are going to be wrong just to find the correct path.
So the QuRL paper proposes using quantization during this phase. Now, my understanding of quantization is that you are essentially lowering the resolution of the numbers. You're using less precise math to go faster.
That is usually the trade-off, yeah. If you drop the precision, say you go from a 16-bit floating point down to 4-bit or 8-bit, the model generally gets dumber.
It loses detail.
Exactly. And in reinforcement learning, this usually leads to something called training collapse. The AI just gets confused because the feedback signals become too grainy to learn from.
So how did they get around that? Because the metric here is a 20 to 80% faster throughput.
Yeah.
How did they get that speed up without the brain damage?
They utilize a technique called adaptive clipping range.
Okay.
So instead of just blindly chopping off the decimal points of the data, the algorithm dynamically adjusts the range of numbers it actually cares about based on the context of the task.
Smart.
It keeps the important signals clear even at that lower precision.
And getting up to 80% faster throughput. I mean, if you were renting a cluster of high-end GPUs, an 80% speed up is basically an 80% discount on your server bill.
Exactly. It proves we can make AI learn faster without sacrificing the smartness of the final model. When you combine that with the robotics update, you really start to see a clear pattern for the win. We are figuring out how to do the heavy learning phase much, much cheaper.
Speaking of bills and efficiency, let's move on to segment B, the developer platform and tooling. Because historically, getting these complex models to run efficiently on actual hardware has been a bit of a dark art.
Oh, absolutely. It has traditionally been the domain of, like, GPU ninjas.
Right.
People who write raw C++ kernels and deeply understand memory pointers and hardware architecture.
But there was an announcement on the NVIDIA technical blog on February 9th that seems to completely democratize this. It's the TensorRT-LLM AutoDeploy feature. It launched in beta.
This is a quality of life update that honestly borders on a full paradigm shift for developers.
Why does it matter so much?
To understand that, you have to look at the old way of doing things. Let's say a researcher publishes a brand new weird model architecture, maybe a Mamba 2 or a DeathNet.
Something non-standard.
Right. If you wanted to deploy that efficiently in a production environment, you couldn't just click a run button.
You had to rebuild the engine to support it.
Manually. You had to have those GPU ninjas write custom C++ kernels. You had to figure out memory caches. You had to do sharding.
Sharding is when you split the model across multiple chips.
Yes, figuring out how to slice the model so half of it sits on GPU 1 and the other half on GPU 2 without creating a massive traffic jam between them. That process took weeks of specialized engineering time.
And this auto-deploy tool essentially acts like a compiler for all of that.
That's exactly what it is. You
Okay.
take an off-the-shelf PyTorch model, just the regular Python code you download from Hugging Face, and AutoDeploy analyzes it and automatically builds the optimized inference engine.
Does it actually work on the complex stuff, or is it just for standard basic models?
Well, they validated it on Nematron 3 Nano. That is a hybrid mixture of experts model. It has very complex routing plumbing, essentially inside the neural net. What used to take weeks of hand-tuning C++ code was done in days, fully automated.
So it completely separates the model design from the hardware deployment mess.
It's the compiler revolution all over again. In the 90s, software programmers stopped writing raw assembly code because compilers finally got good enough to translate C or Java efficiently.
That makes sense.
This is that exact moment for AI. Researchers can now get really creative with new architectures without worrying if the hardware team can actually support them in the real world.
But for the people who do want to get their hands dirty, there was also a quick hit update to CTJS, right?
Yes, version 4.4.0. This dropped on GitHub on February 11th. CTS is the underlying library for high-performance linear algebra. It's the core math that powers everything.
And what happened?
The big news is they released a Python interface for it.
So you can write custom GPU accelerators without actually knowing complex C++1.
Exactly. It severely lowers the barrier to entry for custom GPU acceleration. It's about meeting developers where they already are. If you're a Python native, which almost all AI researchers are, you can now optimize straight to the metal without having to learn a totally new language.
Fantastic. There was one more developer note for this segment, something regarding NIM updates.
Right. On February 12th in the NVIDIA docs, NVIDIA NIM, which are their inference microservices, they now officially support Black Forest Labs Flux models on ARM-based systems.
Flux is an image generator, correct?
A very high-quality one, yes. And running it on ARM-based systems matters because it points directly to edge deployment.
Not massive data centers.
Right, not
Right.
big power-hungry by 86 servers, but more power-efficient hardware. It hints at a very near future where high-end image generation happens natively on devices that consume much less power.
Which is actually a perfect segue into the economics of the hardware itself. Segment C, chips and infrastructure. Let's talk about Blackwell tokenomics.
A great topic.
I do hesitate to use the word tokenomics because it sounds a bit like crypto slang.
It does.
But in this context, it's literally about the cost of intelligence.
It is arguably the single most important metric in the tech industry right now, cost per token.
So this is an NVIDIA blog report published on February 12th, and the headline metric is a 10x cost reduction per token compared to the previous Hopper generation.
Is that a theoretical lab number, or is that what companies are actually paying in the wild?
This is real-world data from the inference providers themselves. Companies like Baton, Deep Infra, Fireworks AI, Together AI.
The folks selling API access.
Exactly. They are the ones reporting up to an order of magnitude cost reduction.
That is a massive deflationary pressure on AI. Does that just mean AI gets cheaper for you and me to use?
Yes, but it changes the fundamental equation of what you can build. It's not just about saving money on your current bill.
How so? If it's cheaper, I just pocket the savings.
Right. Not necessarily. You spend those savings on volume. We call this the shift to always-on agentic AI.
Okay, break that down. If you are paying, say, 20 cents per million tokens, you are going to be stingy. You only trigger the AI when a user explicitly types a question into a chat box.
Right.
But if you're paying 2 cents per million tokens...
You don't have to be stingy anymore.
Exactly. You can have AI agents running constant loops in the background, proactively checking medical records, monitoring server logs, looking for security patterns 247.
Did they have a specific example of that in the report?
They did. They cited a healthcare company called Sully.ai. By moving to open models running on the Blackwell platform, they cut their operational costs by 90%, while simultaneously improving their response times by 65%.
Wow. So that 10x reduction doesn't just lower the monthly bill. It enables an entirely new category of background software that simply wasn't financially viable last year.
We're leaving the training era, where all the capital went into just building the brain. We are officially entering the inference era, where the value comes from using that brain cheaply and abundantly everywhere.
However, as we start deploying these brains everywhere, we inevitably hit the wall of regulation. Which brings us to Segment D: safety, governance, and policy. There was some interesting activity on Hugging Face this week involving the EU AI Act.
Yes, this popped up on the Hugging Face discussions via Crovia Trust on February 13th.
So what happened?
A transparency layer entity called Crovia flagged a few of NVIDIA's model cards, specifically for models like Parakeet TDT and Segformer.
Flagged them for what exactly?
For EU AI Act compliance. They ran a checklist audit and marked the training data transparency section as partial.
Partial. That sounds like a polite corporate way of saying you failed the audit.
I wouldn't go quite that far. It's certainly not a massive scandal. It's more of a friction point. The models do have training sections and documentation, but they didn't explicitly enumerate every single dataset version used in the pipeline.
So it's essentially a paperwork issue.
It is, but you have to realize that in 2026, paperwork is a product feature. This whole event really highlights the collision happening right now between the open weights movement, where you just give the raw model away to the community, and these strict new regulatory environments that demand a flawless pedigree for every single byte of data.
Meaning if you can't explicitly prove where your data came from, you might be entirely locked out of the European market.
Exactly. Proper documentation is becoming just as critical as the model's accuracy. If you are an enterprise integrating AI, you simply cannot use a model that isn't compliant, no matter how incredibly smart or fast it is.
Which is a sobering reality check.
Okay.
But let's pivot from the red tape back to the breakthrough science. Segment E: enterprise adoption and science at the edge.
My favorite segment this week.
We started the show with that 9-month to 4-hour metric. Let's finally unpack that. This was a story on the NVIDIA technical blog on February 10th about live searing science.
Right. This comes out of a major collaboration involving SLAC, that's the Linear Accelerator Center at Stanford, and the Vera C. Rubin Observatory.
So we are talking massive, big science data.
An absolute fire hose of data. Historically, the workflow was incredibly slow. You run the physical experiment, You record terabytes of raw data to tape drives, and then you spend months processing it completely offline.
And if you realize 3 months later that your sensor was slightly out of focus,
Tough luck. You wasted the grant money. And more importantly, you wasted time, which in the scientific community is even more valuable than funding.
so how did they fix it? How do you get from 9 months to 4 hours?
They moved the extreme compute directly to the edge. They were using CuPy and QPNumeric.
Those are the GPU-accelerated Python libraries.
Yes, they use them to process that massive data stream in real time, right as it's generated.
Hence the term live steering.
Exactly. So if an astronomer is looking at a sky survey and the system instantly flags an anomaly, they can adjust the telescope that exact same night. Or if the giant X-ray laser isn't hitting the sample correctly, they can tweak the beam in milliseconds.
So that 4-hour metric isn't just about doing the math faster. It's about completely removing the waiting time between asking the question and getting the answer.
They cited 1100x speedups in some specific analytical pipelines. It turns science from a slow batch process into an interactive one.
Yeah.
You are literally having a real-time conversation with the physical data rather than just reading a dry report about it a year later.
Now, you mentioned edge compute. Usually when we talk about massive AI models or supercomputers, we picture a warehouse full of server racks. But there was a story published on February 12th about DGX Spark units being deployed in some very interesting places.
Ah, the desktop supercomputer.
Right.
It's a box that literally fits on your desk, but it can handle running models up to 200 billion parameters locally.
Which honestly seems like total overkill for a desktop machine.
It does, unless you happen to be working at the South Pole.
Excuse me, the South Pole.
Yes. One of the notable deployments of DGX Spark is at the IceCube Neutrino Observatory down in Antarctica.
I have to imagine the Wi-Fi is pretty spotty down there.
That is exactly the point. You absolutely cannot rely on a cloud connection. You have massive amounts of data coming from these deep ice neutrino detectors, and you have extremely limited satellite bandwidth to the outside world.
So you have to process the data locally.
You have no choice. DGX Spark gives them true data center-grade compute right there on the ice.
It's basically permissionless supercomputing.
That's a great way to put it.
Yeah.
And it's not just the South Pole. It's happening at places like Harvard and Stanford, too. It democratizes the research process. You don't need to write a tedious grant proposal and wait in a queue for 6 months to get time on the massive university cluster just to test a small hunch.
You just test it locally.
Securely, which is huge for medical data. And if the hunch works, then you scale it up to the cloud later.
It's interesting that the theme today keeps coming back to access. Access to optimized code without knowing C++C, access to cheap tokens for background agents, access to supercomputers at the South Pole.
It really has been a remarkably dense week for the ecosystem.
So, just to recap the journey for you listening, we've gone from robots simulating 4,000 parallel worlds at once to compilers that essentially write their own optimization code to the raw price of inference dropping by a factor of 10, and finally, doing real-time neutrino physics on a desk in Antarctica.
A lot of ground covered.
If you had to pull a single thread through all of these distinct stories, what is the ultimate takeaway?
The overarching theme of this week is the acceleration of the workflow itself. We tend to obsess over faster silicon chips, but chips are just a means to an end. This week was fundamentally about removing friction.
Friction in every step of the process.
Right. Whether that friction is the literal financial cost of running a token, the sheer difficulty of writing complex kernel code, or the agonizing 9-month wait for scientific data analysis.
It feels like we are completely removing the waiting room from innovation.
Precisely. The time between I have an idea and I know if it works is collapsing to zero. And when that feedback loop gets tight enough, innovation starts to look instant.
Well, here's my final thought for you to mull over as we wrap up. We've seen today that tools like AutoDeploy are automating the deeply complex optimization work that used to require a team of highly paid PhDs.
Yeah.
And at the exact same time, the hardware costs to run these models are dropping by 90%. So are we about to see a massive, unprecedented surplus of AI applications flooding the market simply because the traditional barrier to entry just completely evaporated?
I mean, if you don't need to be a coding wizard and you don't need millions of dollars in venture capital just to run these models,
Who doesn't build an AI at that point?
that is the trillion-dollar question right now.
Definitely something to explore on your own. Thanks for diving deep with us today.
We'll see you next time.